So in the last class I have told you that for a solution showing positive deviation, if you plot boiling point versus composition, okay, you will get the boiling point curve which will be appear below, right, below this ideal line, and there is a boiling point for a particular mixture which is having the lowest possible value, right, among all the composition. This composition has the lowest boiling point, and this composition or this mixture is what we call as azeotropic mixture having minimum boiling point or minimum boiling azeotropic mixture. Okay, so this mixture is called minimum boiling azeotropic mixture. Minimum because it has lowest boiling point, so it is called minimum boiling azeotropic mixture. So keep this in mind. Non-ideal solution showing positive deviation, okay, will give low boiling azeotropic mixture, also called minimum boiling azeotropic mixture. Okay, so this is a very important point. And what is azeotropic mixture? Last class I have told you, in azeotropic mixture the composition in the liquid phase and the composition in the vapor phase are same. Okay, here I have given percentage composition. See, percentage of A and percentage of B in the liquid phase 40, 60. So I have taken like this. Okay, just for understanding purpose. If same percentage of A and B exist in the vapor phase also, we call that mixture as azeotropic mixture. Okay, you can even take mole fractions, mole fraction of A and mole fraction of B, right, in the liquid phase, and mole fraction of A and mole fraction of B in the vapor phase. Okay, so suppose if A mole fraction is, say, for example 0.2, okay, here also the A mole fraction is 0.2, right, and B mole fraction, suppose if it is 0.8, right, this is also 0.8. So what does it indicate? It indicates that composition in the liquid phase and composition in the vapor phase are same. Okay, if the compositions are same, then we call the mixture as azeotropic mixture, right? Azeotropic mixture is called constant boiling mixture. It is also called constant boiling mixture. I have told you what's the meaning for constant. Constant means the composition in the liquid and composition in the vapor are same. That's the meaning for constant here. Okay, and it cannot be separated by simple distillation techniques. If you want to separate an azeotropic mixture, if you want to separate A and B from an azeotropic mixture, you have to adopt some special techniques. Okay, we have azeotropic distillation techniques also there. We have to follow that. Okay, now, so what we discussed is that this is the point I have given in the last class. So keep this in mind. Non-ideal solution, okay, showing positive deviation. Positive deviation means deviation from ideal behavior. In this case, if you plot vapor pressure versus composition diagram, vapor pressure versus composition, I have plotted mole fraction of B here. So here mole fraction of B is 0, here mole fraction of B is 1. Suppose if vapor pressure of B, pure vapor pressure of B is greater than pure vapor pressure of A, okay, then for solution showing positive deviation, if this is the ideal line, then for positive deviation you will get a curve which will go above this straight line. Okay, so the vapor pressure, total vapor pressure of the solution, right, is greater than the ideal line, okay, for all composition. Whatever composition you take, okay, the total vapor pressure is greater than the ideal line. Okay, we call this type of solutions as solution showing positive deviation. Right? This is actually total vapor pressure curve. Even you can draw partial vapor pressure of A, right, and partial vapor pressure for B also. This is partial vapor pressure for B, and here the partial vapor pressures of A and B also will go above this curve. Okay, so what does this indicate? It indicates that whether you plot total vapor pressure or partial vapor pressures, they always go above the ideal line. Above these dotted lines are ideal lines, so it will go above the ideal line. If it appears like this, we call that solution as solution showing positive deviation. Then this is actually called vapor pressure composition diagram. Okay, vapor pressure composition plot for solution showing positive deviation. Now I'll show you another important plot. Okay, this is actually boiling point composition plot. Boiling point composition plot. Anyway, we discussed in the last class. I'll just brush up before begin further. Okay, so here I have told you if vapor pressure is high, boiling point will be low. Okay, so this is the pure boiling point of pure liquid B, and this is the boiling point of pure liquid A. Higher the vapor pressure, lower will be the boiling point. Lower the vapor pressure, higher will be the boiling point. That's the point. Okay, and here students observe this carefully. For solution showing positive deviation, okay, you will get a curve will appear like this. Okay, and this is this black color line. It gives you mole fractions of B, right, in the liquid phase. Okay, this curve gives you mole fractions of B in the liquid phase. Suppose if I plot mole fraction of B in the vapor phase also in the same diagram. Okay, mole fraction of B in the vapor phase, right? Then the curve will something appears like this. Okay, I have drawn like this. Students, observe this carefully. This is for vaporous curve, and this is for liquidous curve, liquidous. What I am trying to say here is, listen, in this diagram I have shown both. That is, for different you take different mixtures of liquid A and B, and plot the mole fraction of B, right? Mole fraction of B versus boiling point. Okay, in the y-axis we have boiling point, in the x-axis I have plotted mole fraction of B. XB is the mole fraction of B in the liquid phase, and YB is the mole fraction of B in the vapor phase. Okay, students, observe this carefully. Here at all composition, suppose if I take a particular composition here, observe carefully. If I take some composition here, at this composition, right, or I'm sorry, instead of I'll take some boiling point. I'll take some boiling point here, right? At this boiling point, I'll draw a line here. I'll draw a straight line. This straight line cuts your liquidous curve and the vapor curve at a different points. So this is the liquidous curve point, and this is the vapor curve point, and this is the mole fraction of B in the liquid, and this is the mole fraction of B in the vapor. Mole fractions of B in the liquid and vapor are different. See this, students, observe carefully, because you have taken some boiling point. Okay, some boiling point. At this boiling point, the mole fraction of B in the liquid phase and mole fraction of B in the vapor phase are different. But at this boiling point, see, this boiling point is the minimum boiling point. See here, at this boiling point, right, the vapor pressure, the vapor curve, vaporous curve, and the liquidus curve, they meet at this point. So at this point, the composition or the mole fraction of B in the liquid phase and mole fraction of B in the vapor phase are one and the same. Students, is this clear? Are you able to follow this? Hello? Students, are you able to follow?
Yes, sir.
Yeah. See, students, I have drawn the mole fraction of B in the liquid phase and mole fraction of B in the vapor phase, both in the same diagram. Okay, versus boiling point I have plotted, right? And this below line indicates liquidus line and the above line indicates vaporous line. Right? If you take any boiling point, any other boiling point, okay, the mole fraction of B in the liquid phase and the vapor phase are different. But exactly at this boiling point, called the minimum boiling point, at this lowest possible boiling point, the mole fraction of B in the liquid phase and mole fraction of B in the vapor phase are one and the same. That composition is what we call as azeotropic mixture. Azeotropic mixture. And this azeotropic mixture has the lowest possible boiling point, so it is called minimum boiling azeotropic mixture. Okay, so this is very, very important point. Keep this in mind. This is called minimum boiling azeotropic mixture. Here I like to put some informations. You have to keep this in mind. Students, non-ideal solutions usually, okay, if the deviation is large, right here, non-ideal solution, right, usually should form azeotropic mixture. They form azeotropic mixture. Students, I like to make one point here. Not all non-ideal solutions form azeotropic mixture. I'm not saying like that. If the deviation is large, those non-ideal solution will form azeotropic mixture usually. Okay, if the deviation is large, right? Now, if the non-ideal solution shows positive deviation, then you will get minimum boiling azeotropic mixture. Okay, so for positive deviation you will get minimum boiling azeotropic mixture. Nice example is that. And remember, azeotropic mixtures, right, have definite composition. Azeotropic mixture has a definite composition, right? Mixture has definite composition. Exactly at one particular composition you will get azeotropic mixture. Say for example, let me write to the next page. Students, observe this carefully. Suppose if you take ethanol and water mixture, ethanol plus water, I'll take this mixture, right? From ethanol water mixture you can get pure ethanol, or you can get ethanol by simple distillation. Okay, but once it reaches a particular composition, say for example percentage by volume of ethanol. Suppose I have some solution in which percentage by volume of ethanol, suppose if it reaches 95%. Okay, that means 95% of ethanol is there and remaining 5% is water. Once you reach this composition, then you will get azeotropic mixture. and I have told you whenever alcohol is present, what type of deviation will get? Last class I have told you, whenever alcohol is present, students keep this in mind. If alcohol present, then usually the solution shows positive deviation. Okay, so it's a simple trick, keep this in mind. Whenever alcohol is present, usually the solution will show positive deviation. Positive deviation means I'll get minimum boiling azeotropic mixture. I'll get minimum boiling azeotropic mixture. Okay, we'll get minimum boiling azeotropic mixture, and this is the composition of the ethanol water azeotropic mixture. Once 95% by volume of ethanol and 4% by volume of water, if that mixture is attained, then it is not possible to separate ethanol and water by simple distillation. Students, is this clear? Any doubt in this? Any doubt?
No, sir.
Yeah. Students, all of you turn on your camera. Hello, students? Yeah, turn on your camera. Yeah. So this is regarding positive deviation. Now, let me go to the next one called negative deviation. Non-ideal solution. Non-ideal solution showing negative deviation from ideal behavior. Okay, non-ideal solution showing negative deviation. What is meant by that? If suppose I'll take two liquids, suppose I'll take two liquids A and B. I'll take liquid A and liquid B. Okay, I'll mix them and I'll form a solution. I'll form a solution containing A and B. Right? If the force of attraction between AB, okay, if the force of attraction between AB, if it is greater than the force of attraction between AA or the force of attraction between BB, okay, if the AB attraction is stronger, right, then the solution will exhibit negative deviation. That is, in this case, total vapor pressure which is observed or experimentally measured will be less than the total vapor pressure which is calculated using Raoult's law. You calculate total vapor pressure using Raoult's law and you measure the total vapor pressure through experiment. If the experimental total pressure is less than the total, okay, you will get a solution showing negative deviation. So in this case, you will get negative deviation. So students, keep this in mind, very, very important. If the force of attraction between A and B is strong compared to AA or BB, then you will get negative deviation. Okay, so for negative deviation, let me draw the next page. This is the first point you should keep in mind. Right. Okay. Now, what about delta V mixing? Since there is a strong force of attraction exists between AB, okay, total volume, that is volume of liquid A plus volume of liquid B, this is total volume before mixing. This is total volume before mixing. Okay, now I'll mix the two and form a solution, total volume of the solution. This is total volume. This is total volume after mixing, total volume after mixing. Students, observe this carefully. If the AB attraction is strong, this is what I said, right? If the AB attraction is strong compared to AA or BB, okay, so what will happen? The molecules comes closer. Okay, AB attraction is strong, so molecules comes closer and closer and closer. Therefore, the volume of the solution get reduced. So, if I take delta V mixing, what is delta V mixing? It is nothing but volume of the solution, that is total volume after mixing minus total volume before mixing. Total volume before mixing. If we take this difference, students, listen carefully. Here this is low and this is high. Why this is high? Because here we are taking AA separately, BB attraction separately. But when you mix them, AB attraction is very strong. Therefore, the molecules comes closer. Okay, if the attraction is strong, molecules comes closer and closer and closer. So total volume reduces. Okay, so here volume reduces. Reduction in volume occurs. Reduction in volume occurs due to strong force of attraction between AB. Therefore, this volume, that is total volume after mixing, is low compared to total volume before mixing. So this is low, this is high, therefore I will get negative sign. So delta V mixing is negative for solution showing negative deviation. Okay, similarly, what about delta H mixing? Delta H mixing, right? What about this? Yeah, I have told you whenever attraction exists, students, now A and B, okay, attract very strongly. So whenever attraction exists, okay, there will be release of energy. Okay, listen. When attraction, right, when force of attraction between A and B, okay, if the force of attraction between A and B is strong, is very high, is high or very high, what will happen? Heat is released. Heat is released. Students, keep this in mind. If force of attraction is weak compared to AA or BB, in that case, heat is absorbed. When force of attraction is very high, heat is released. Okay, you know very well, if heat is released, we call that process as exothermic process, right? This is exothermic. It is an exothermic process. For exothermic process, delta H is negative. So delta H mixing is negative for negative deviation. Students, is this clear? Remember, if attraction increases, heat will be released. If attraction decreases, heat is absorbed. This is the point. So in solution showing negative deviation, okay, in solution showing negative deviation, the force of attraction between AB is very high compared to AA or BB. Therefore, when force of attraction increases, okay, if force of attraction is very high, then heat is released. Okay, the process where heat is released is called exothermic process. For exothermic process, delta H sign is negative. So delta H mixing is negative for solution showing negative deviation. Okay, then what about delta S mixing? So before that, I'll discuss delta G mixing. So what about delta G mixing? I have told you, by mixing liquid A and liquid B, okay, we are getting solution. Solution is formed spontaneously. Therefore, delta G mixing should be negative. Okay, suppose if A and B, they do not mix and form separate layer, in that case delta G mixing is not negative, okay, because there is no solution. But what I am saying is, suppose you take liquid A and liquid B, mix them, if you get a homogeneous solution, that means the process occurs spontaneously, right? Whenever the process occurs spontaneously, then delta G mixing should be negative. Okay, liquid A and liquid B form solution. Liquid A, I'm mixing liquid A and liquid B. They form solution spontaneously, right? They form solution spontaneously. For any spontaneous process, delta G should be negative. Simple. For any spontaneous process, delta G should be negative. Okay, students, is this clear? Any doubt in this? If they do not form, yes, any doubt?
No, sir.
Okay, ma'am, right. If they do not form any solution, then delta G mixing, okay, is positive. But since they form solution spontaneously, delta G mixing should be negative. Okay, then what about the next one? That is delta S mixing. How to fix it? Delta S mixing, yes, it is very easy. Yes, how to do that? You know very well, delta G mixing equal to delta H mixing minus T into delta S mixing. Okay, and we fix the delta G mixing sign. Delta G mixing is negative. Okay, and what about delta H mixing? That also we fixed already. Delta H mixing is also negative, right? Delta H mixing is also negative. So this is also negative. And you know very well, temperature is a positive quantity because we are going to take temperature only in Kelvin. So temperature is positive. Therefore, to get this negative, students observe carefully. To get this negative, what happens if this is negative, students? What will happen if this is negative?
It will become positive.
Yeah, so negative means negative into positive is negative, negative and negative become positive. So this is become positive and this become negative. Okay, then in that case the magnitude will decide whether delta G mixing is negative or positive. But if this is, suppose if this is positive, then what will happen, students?
It is negative.
Yeah. Okay.
Negative.
Yeah, if this is positive, then the whole right hand part become negative always. Negative always. Okay, so what does this indicate? It indicates that delta S mixing should be positive to get solution showing negative deviation, okay, with any liquid pairs, with any liquid A and B. If you want to form if any liquid A and B form negative solution form negative deviation, okay, then delta S mixing should be positive, right? If delta S mixing is negative, then you have to see the magnitude and decide. That is somewhat tough task. So what we usually take is delta S positive, because if this is positive, right, then the mixture is always shows negative deviation, right? Simple. Students, is this clear? Any doubt? If you find any difficulty, you tell me. Right. Okay, so I have given the characteristic features of solution showing negative deviation. Now I'll give some examples. Okay, what are the examples for solution showing negative deviation? Right, examples. Okay, let me take the simple example: HCl plus water. HCl plus water. Students, observe carefully. In water, we have hydrogen bonding attraction. If any two liquid pair is given, first you identify what type of attraction exists. In water, we have hydrogen bonding attraction. In pure HCl, students, if you take pure HCl, we have dipole-dipole attraction. Pure HCl has dipole-dipole attraction. Water has hydrogen bonding attraction. But if you mix these two, what will happen? Okay, students, HCl will undergo ionization and it will donate H plus to water. So water will receive the H plus and become H3O plus ion, and the chloride become Cl minus ion. So now in solution we have positive and negative ions. Students, observe carefully. Before mixing, pure water shows only hydrogen bonding attraction. Pure HCl shows dipole-dipole attraction. But if you mix them, okay, HCl will ionize. HCl ionizes and donate H plus. Okay, therefore you will get H3O plus ion. It will donate H plus to water. So water takes H plus and become H3O plus. And chloride
Sir,
forms chloride. Yes, yes.
sir, how to find the type of attraction, sir?
Yeah. For hydrogen bonding, anyway we are going to discuss this, but no problem, I will tell you how to do that. Listen, whenever hydrogen is attached to more electronegative element like fluorine, or hydrogen attached to oxygen, or hydrogen directly attached to nitrogen, right? Students, observe this carefully. Whenever hydrogen attached to more electronegative element like fluorine, or hydrogen attached to oxygen, or hydrogen attached to nitrogen, okay, those molecules shows hydrogen bonding. So in water, you know very well the structure of water is this. So hydrogen atom is connected to oxygen directly, correct? Whenever hydrogen atom connected directly to fluorine or oxygen or nitrogen, those compounds will show hydrogen bonding. So water molecule will show hydrogen bonding. Okay, in HCl, hydrogen is connected to chlorine. This hydrogen does not show any hydrogen bonding because it is connected to chlorine. Right? Now, students, observe carefully. Since the two atoms are different atoms, okay, the one which is more electronegative, so here chlorine is more electronegative, that gets partial negative charge, and the hydrogen get partial positive charge. I will get a dipole. I have told you pole means charge. I have two poles now, so it is called a dipole. Dipole. One dipole and the other dipole are attracted through the partial charges. See, this partial positive charge on one dipole and partial negative charge on another dipole, between that there is an attraction. This attraction is what we call as dipole-dipole attraction. So in HCl we have dipole-dipole attraction. In water we have hydrogen bonding attraction. In the last class I have told you hydrogen bonding attraction is stronger than dipole-dipole attraction, right? You might have remember that. Anyway, I'll write here. Students, remember this, very very important. Ion attraction is stronger, very stronger than ion dipole attraction. Which is stronger than hydrogen bonding attraction? Hydrogen bonding attraction is stronger than dipole-dipole attraction. Okay, and like that goes. Dipole-dipole attraction, then London forces. This is the order. So here in our in the given liquid pair, water molecule shows hydrogen bonding, HCl shows dipole-dipole attraction. Okay, now after mixing these two, students, what we are getting here are ions, right? I am getting hydronium ion and chloride ion. Ion attraction is very strong, you know very well. Ion attraction is strong. So AB attraction is, students, after mixing these two I am getting AB. AB attraction is
Strong.
very strong. Whenever AB attraction is stronger than AA or BB, then you will get solution showing negative deviation. So HCl and water, if you mix, you will get hydrochloric acid solution, right? If you mix HCl and water, you will get hydrochloric acid solution. Hydrochloric acid solution shows negative deviation. Is this clear, student? Any doubt?
No doubt, sir.
Okay, yeah. Then next one. Number 2, example number 2. We have plenty of examples. Nitric acid HNO3 plus water, right? Nitric acid, in pure nitric acid, yes, we have hydrogen bonding. in water also, because this is the structure of nitric acid. And let me draw like this. This is the structure of nitric acid. Students, here see, hydrogen is connected to, hydrogen is directly attached to which atom?
Oxygen.
Will it show hydrogen bonding? Yes. So here you will get hydrogen bonding. What about in water? Hydrogen, yes, here also you will get hydrogen bonding. So nitric acid and water both will show hydrogen bonding separately. But if you mix them, I will get H3O plus ion. Nitric acid donate this hydrogen as H plus to water molecule. So water molecule gains the H plus and become H3O plus. And I'll get NO3 minus ion. NO3 minus ion. So I'll get ions now. Ion-ion attraction is very strong. Therefore,
Negative deviation.
yes, that's all. You will get solution with the negative deviation. Keep this in mind. Generally, if water and acid mixture is given, they usually form negative deviation. Okay. Similarly, I'll give another example. See, number 3, water plus formic acid. Formic acid. Yes, this will give negative deviation. Number 4, plenty of examples are there. Chloroform and benzene. Students, this is actually an exceptional example you should keep in mind. Chloroform and water. Okay, what type of attraction is there? See, in chloroform we have only dipole-dipole attraction, right? CH Cl3. This is chloroform, and hydrogen has partial positive charge, this carbon has partial negative charge, so we have dipole-dipole attraction only between one molecule and other molecule. In benzene we have pi electron cloud, so between one benzene and another benzene, okay, there is a pi repulsion is there. Okay, but the moment you mix these two, what will happen? The chloroform molecules, right, this end, the positive end of the chloroform molecule is attracted by the pi electronic charge of benzene. There is an attraction between these two. Between chloroform and benzene, there is an attraction through dipole and pi electrons. Okay, here we have pi electrons. Between pi electrons and the positive part of dipole, there is an attraction. Because of this attraction, the solution shows negative deviation. Very nice example. Keep this in mind. Chloroform and benzene form solution with a negative deviation. Okay, very, very important. Then we have a lot of example actually. We have acetic acid plus pyridine. This is acetic acid and pyridine. This is the formula for pyridine. Let me write like this. This compound is called pyridine. 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 If you mix acetic acid and pyridine, this is acetic acid. I am giving you common name, and you know very well for organic compounds we have common name as well as IUPAC name. Here I am giving you only a common name. Okay, and the IUPAC name is, we have 2 carbon atom, so it is ethanoic acid. So ethanoic acid and pyridine, this mixture will form negative deviation. Okay, I'll give a few more example. Then example number 6, acetone CH3 CO CH3. This compound is called acetone or propanone. Acetone plus aniline. This compound is called aniline. Benzene, to this you attach an NH2 group. This compound is called aniline. Acetone and aniline, students observe this carefully. Acetone and aniline also form solution with a negative deviation. Acetone and aniline. Okay, yeah, these are all few examples which shows negative deviation. Okay, now let me draw and show you how the vapor pressure composition.
Sir?
Yes, yes.
Sir, can you explain the example first, sir?
Example 4. Okay, one second. Example 4. Yeah. See, in chloroform, this hydrogen has partial positive charge. This carbon has partial negative charge due to electronegativity difference. Okay, so I have dipole. Therefore, between one molecule and another molecule, there will be dipole-dipole attraction. In chloroform, we have dipole-dipole attraction. In benzene, between one benzene molecule and another benzene molecule, there is a weak repulsion because of pi electronic cloud. Okay, here I have pi electron cloud electrons. Pi electrons are there. Here also we have pi electrons. So since the ring contains pi electron cloud, when the two benzene molecule comes closer, there is a small repulsion exists. But when you mix benzene and chloroform, what happens is that the pi electron cloud in benzene and the partial positive charge of hydrogen in chloroform, between these two there is an attraction. Students, see this, because I have pi electron cloud. Electron means negative, right? Negative, and this is positive, so there is an attraction. This attraction is stronger compared to these two in this case. This attraction is stronger compared to the attraction in chloroform. Therefore, you will get solution with the negative deviation. It's a very nice example actually. Right? Take two. Is it clear? Any doubt? No? Here?
Yes, sir, clear.
Yeah. Right. Now. So now let me show the vapor pressure composition diagram for solution showing negative deviation. Okay. Vapor pressure composition plot. Okay. Diagram or plot. Okay. So I'll take vapor pressures in y-axis. Vapor pressure in y-axis, and composition. Let me plot mole fraction of B, right, in the liquid phase. Okay, in the x-axis, right. Here xb is 0. Here xb is 1. xb 0 means we have pure A. Okay, so let us assume this is the vapor pressure of pure A, right, and if xb is 1 means we have pure liquid B. For pure liquid B, let us assume the vapor pressure of B is here. So in this case, I have assumed that vapor pressure of pure B is greater than vapor pressure of pure A. If I join the two using a straight line, okay, this straight line indicate ideal solution. Okay, similarly, if I join this here to here, I'll get partial vapor pressure of A for ideal solution, and here to here, I'll get partial vapor pressure of B for ideal solution. So these straight lines are for ideal solution. But now our solution show negative deviation. Okay, negative deviation means vapor pressure is lesser than the ideal. So we should plot a graph like that, like this. You'll get a negative deviation. See, it goes below. Similarly, this is total vapor pressure, right? This line is for total vapor pressure. Total. Okay, similarly we have negative deviation here also, negative deviation here and negative deviation here. Alright, students, is it clear? The dotted lines indicate ideal solution lines, and the curves, like solid curves, are for the solution showing negative deviation. So in the vapor pressure composition diagram, if the vapor pressure lines goes below ideal line, okay, it means the solution shows negative deviation. Right? Suppose if I plot temperature composition diagram, let me draw in the next page. Temperature composition diagram, how the temperature means boiling point. Suppose if I plot boiling point, I'll write shortly BPT, boiling point composition diagram. Boiling point composition diagram. If I plot, yes, the plot will appear like this. Okay, so here see in the vapor pressure composition diagram, students, in the vapor pressure composition diagram, vapor pressure of pure B is high, vapor pressure of pure B is high, vapor pressure of pure A is low, right? But if you plot boiling point of pure B will come down and boiling point of pure A will go up. Okay, so this is boiling point of pure B and this is boiling point of pure A, because you know very well boiling point and vapor pressure are inversely proportional. Okay, now I'm going to plot mole fraction of B in the liquid state and mole fraction of B in the vapor state also. Students, observe carefully this, very important. I'm plotting both. Okay, mole fraction of B in the liquid phase, mole fraction of B in the vapor phase in the same diagram, within the same diagram. How the diagram will look like. Okay, since solution shows negative deviation, the boiling point of the solution will be more, okay, at different compositions. Okay, so let me show like this. The curve, right? This is one curve, this is another curve. It will go also like this. Okay, students, observe this carefully. The above one, right, is the vaporous curve, vaporous curve, and the below one is the liquidous curve, Now the point that you have to note here is, if you take any boiling point, right, say for example I'll take some boiling point here, some boiling point T. Now you draw a straight line, from this point. Now see, the straight line cuts the liquidous curve and the vaporous curve at different composition, right? So here the mole fraction of B in the liquid state is different from the mole fraction of B in the vapor state. So if you take any boiling point, just like that, any boiling point, the vapor pressure composition and the composition in the liquid phase and the vapor phase are different. But see this boiling point, this is the maximum boiling point. At this boiling point, the liquidous curve and the vaporous curve meet. Therefore, exactly at this boiling point, right? Exactly at this boiling point, you can show in this side also. Exactly at this boiling point, the mole fraction of B in the liquid phase and mole fraction of B in the vapor phase are exactly same. We call that mixture as azeotropic mixture. This mixture is called azeotropic mixture. But is it minimum boiling point mixture or maximum, students? Is the boiling point minimum or high? High. So it is a maximum boiling point mixture. So let me write here, maximum boiling azeotropic mixture. This is maximum boiling azeotropic mixture. So point is very clear. For solution showing positive deviation, you will get minimum boiling azeotropic mixture. Whereas for solution showing negative deviation, we will get maximum boiling azeotropic mixture. Okay, students, is this clear? Any doubt?
No, sir.
Yes, yes, take two. And the nice example is actually we have a lot of examples, but the example that is given in your book is actually HCl and water. No, I'm sorry, nitric acid and water, I think so. Yeah, nitric acid and water. Nitric acid and water mixture is given. Okay. In this mixture, at what percentage you will get azeotropic mixture? Okay, if a mixture contains 68% of nitric acid, whenever a mixture contains 68% of nitric acid and 32% of water, this is by mass. Okay, by mass, 68% by mass of nitric acid and 32% by mass of water. Okay, once this mixture is attained, we call that mixture as azeotropic mixture. Suppose you take some mixture of nitric acid and water, some mixture, okay, and start to distillate it. Okay, start to distillate. Distillate means separate, right? If you do separation continuously, at one stage you will reach this mixture, this composition. Once this composition is reached, then you cannot separate them. You cannot separate nitric acid and water by simple distillation method, because you got azeotropic mixture. Okay, and for this azeotropic mixture, the minimum boiling point, the maximum boiling point is 393.5 Kelvin. Okay, for this mixture, for nitric acid and water mixture, once it form azeotropic mixture, the boiling point of the azeotropic mixture is 393.5 Kelvin. Okay, is it clear, students?
Yes, sir.
Right? Yeah.
Yes, sir.
Okay, so with this we have completed ideal and non-ideal solutions. Now let me summarize them so that you will get some clarity on the topic. Let me summarize everything here. So we have ideal solution. Students, observe carefully. We have ideal solution and we have non-ideal solution. Okay, we have ideal and non-ideal. In non-ideal, we have solution showing positive deviation. We also have solution showing negative deviation. Okay, ideal and non-ideal. Now what I'm going to do, I'll just list out some of the essential points here. Point number 1. For ideal solutions, students, observe carefully. Total pressure, observed total pressure is equal to calculated total pressure. They are equal, right? Whereas for non-ideal solution, right, for non-ideal solution, if solution show positive deviation, the observed total pressure is greater than the calculated total pressure. For solution showing negative deviation, the observed total pressure is less than the calculated total pressure. Okay, students, is this clear? Any doubt? Any doubt? This is the first point. Second point, in this case, force of attraction between AB and force of attraction between AA and force of attraction between BB, right, all are roughly equal for ideal solution. Whereas for non-ideal solution, okay, showing positive deviation, force of attraction between AB is less compared to force of attraction between AA or force of attraction between BB. Whereas for solution showing negative deviation, force of attraction between AB, right, is strong compared to force of attraction between AA or force of attraction between BB. Very important. Okay, then point number 3, delta V mixing is 0 for ideal solution. For solution showing positive deviation, delta V mixing is positive. For solution showing negative deviation, delta V mixing is negative. Okay, then next point, delta H mixing. Delta H mixing is 0 for ideal solution. Okay, for non-ideal solution, delta H mixing is positive for positive deviation and delta H mixing is negative for solution showing negative deviation. Okay, the next point, delta S mixing. Yes, it is positive, positive, and here also it is positive. Okay, then delta G mixing, delta G mixing is negative for ideal solution as well as for non-ideal solution. Delta G mixing is negative here, and here also it is negative. It's negative. Okay, students, very essential points you should keep in mind. And another important point here is ideal solution does not form azeotropic mixture. Ideal solution does not form azeotropic mixture. Now only non-ideal solution should form azeotropic mixture, and non-ideal solution showing positive deviation will give minimum boiling azeotropic mixture. I'll put simply AM. AM means azeotropic mixture here. Minimum boiling azeotropic mixture. For non-ideal solution showing negative deviation, I'll get maximum boiling azeotropic mixture. Okay, students, is this clear? Any doubt? Any doubt? Yes, keep it in mind. Very important. You must know the differences, and you should also know the vapor pressure composition diagram for all these cases. Okay, yeah, yes. With this, we have completed ideal and non-ideal solution, right? Then what we are going to do next is there any doubt in this, students? Do you have any doubt in this?
No, sir.
No, sir.
Now let me start. Solution containing non-volatile solute. Students, so far we have discussed liquid solution, right? We have taken two liquids and we formed a solution. Okay, now what I'm going to do, I'm going to take a solution containing, see, so far what we discussed, we took two liquids. So far we discussed that we took two liquids, both are volatile. This is volatile, this is also volatile, both are volatile, and we formed a solution, right? Okay, but now what I'm going to do, I'm going to take a solvent and a solute. I'm going to take solvent and solute. You know very well, solvent means the one which form major proportion in solution. Solute means the one which form minor proportion. Okay, I'm going to take a solvent and solute, and the solute should be non-volatile. It does not form vapor. That's all. That's the point. The solute is non-volatile now, and we are going to form solution from this. Okay, this is the solution we are going to discuss now. Solution in which solute is non-volatile, right? So what I'm trying to say, suppose you take a pure solvent, solvent alone, pure solvent. Okay, at any temperature T, or at a particular temperature T, the solvent molecule will go to vapor state, so that you'll get vapors. Evaporation takes place first, then after that you'll get condensation, and after one stage you'll get equilibrium, right? Rate of evaporation and rate of condensation become equal. You will get equilibrium. At the equilibrium, you measure the vapor pressure of this liquid. Okay, the vapor pressure above the liquid. Okay, let me take it as vapor pressure of pure solvent. Okay, so pure means I'll put a not symbol, pure, and this is vapor pressure of pure solvent. For solvent, I'll put number 1. Number 1 indicates solvent, right? I have told you already. In solution topic, number 1 means solvent, number 2 means solute. Okay, this is pure solvent. Now what I am going to do, students, observe this carefully. Now I'll take this pure solvent, I'll put some amount of non-volatile solute in this. Okay, so now we have solution. I have solution containing non-volatile solute. We have solution containing non-volatile solute. Okay, now what happens here, students? Observe this carefully. The non-volatile solute molecules also occupy the surface. Students, observe very carefully. Very, very important point. In pure solvent, the entire surface of the liquid is occupied by solvent molecules alone. Therefore, more solvent molecule will go to vapor state. Okay, because all the surface is occupied by solvent molecules. Whereas here now listen, some surface molecules are solute molecules. Solute molecule occupies some of the surfaces. Those surface areas are not available for the solvent molecule to go to the vapor state. Solute molecule cannot go because they are non-volatile. They never go to vapor state. So here also, in the solution also, only solvent molecule to go to the vapor state. But there's a problem. What's the problem? Some of the surface is covered by solute molecules, which will never allow solvent molecule to go up. Okay, therefore what happens here is, you will get, see here also I'll get vapor. Okay, I'll get vapor pressure of solvent alone. But what I'm saying is, this is vapor pressure of solution. Vapor pressure of solution. Okay, I'll call this as vapor pressure of solution. I'll put P alone. I'm sorry, I'll just put P. What is P here? P is vapor pressure of solution. But we know very well, this vapor is also formed by solvent molecule alone. Is this clear, student? Because solute is non-volatile. Solute molecule cannot go to vapor state. Only the solvent molecule should go. Since this vapor pressure is for solution, I am just using the symbol P. P means vapor pressure of solution. P1 naught means vapor pressure of pure solvent. Okay. Since here also I have solvent molecule, here also I have solvent molecule in the vapor state, it is not necessary to put one and all. Why? Because it is very clear for me that the vapor is occupied by only solvent molecules, whether it is solvent or solution. Am I right, student? Whether it is solvent, okay, or a solution, the vapor state is occupied by only solvent molecules. So this 1-2 representation is not required here. P naught means vapor pressure of pure solvent. P means vapor pressure of solution. Now my question is, among the two, which one is greater and which one is lesser? P or P naught? P means vapor pressure of solution. P naught is vapor pressure of pure solvent. Which one is greater?
P naught.
Yes. Students, observe this carefully. Whenever you add a non-volatile solute, vapor pressure of solution decreases compared to vapor pressure of pure solvent. Whenever you add a non-volatile solute to a pure solvent, and if you form a solution, the vapor pressure of solution will decrease. So vapor pressure of solution is lesser than the vapor pressure of pure solvent. Okay. Now I am going to apply Raoult's law to this. So according to Raoult's law, for solution containing non-volatile solute, okay, vapor pressure of the solution, students, according to Raoult's law, vapor pressure of a solution containing non-volatile solute, according to Raoult's law, vapor pressure of a solution containing non-volatile solute, okay, is directly proportional to the mole fraction of solvent, directly proportional to the mole fraction of solvent present in the liquid phase, present in the liquid phase. Students, is this clear? Any doubt? Why I am taking only solvent here? Why we are focusing on mole fraction solvent alone? Why not solute? See, vapor pressure of solution is directly proportional to mole fraction of solvent alone. Why? The reason is solute is, see this, solute is
non-volatile.
yeah, solute is non-volatile. It never goes to vapor state, correct? It never goes to vapor. Therefore, the vapor pressure of solution is directly proportional to mole fraction of solvent present in the liquid phase. Okay, so I can write like this: vapor pressure of solution is directly proportional to mole fraction of solvent present in the solution. What is x1, students? What is x1? 1 means, yes, mole fraction of solvent. Mole fraction of solvent. Okay, or if I equate this, we should introduce a constant. That constant is P naught. What is P naught here, students? What is P naught?
Partial pressure.
No. It's not partial pressure. The vapor contains only solvent, right? So you should not use the word partial.
Vapor pressure of pure solvent.
Very good, that's all. P naught is vapor pressure of pure solvent. P is vapor pressure of solution. Keep this in mind. Whenever you add non-volatile solute, your solvent as well as solution contains solvent molecules in the vapor state. Is it clear? Okay, so keep this point in mind. This is applicable for solution containing non-volatile solute. Okay, this Raoult's law is applicable for solution containing non-volatile solute. Okay, for this you can use this formula, right? Keep this in mind, very important. Okay, yeah, I stop here. In the next class we are going to discuss what is called colligative properties. This is the last part of this chapter. We'll discuss that in the next class. I stop here.